that seems a little bit inscrutable at this point in time. Hopefully it won't be by the end of this presentation. So first of all, what exactly is an electrodynamic tether, or an EDT? It's a primary satellite and a counterweight that is connected by an electrically conductive tether. As you can see in this diagram, there's the primary satellite at the top, the counterweight down at the bottom, and the solid red line is the tether that is connecting the two of them. Now, electricity is driven through the tether, and when the EDT is within a magnetic field, this generates a force, allowing the EDT to change its orbit. Now, one thing that the satellite must be capable of is emitting and gathering electrons at both the counterweight and at the primary satellite, so that the current is traveling only in one direction along the tether. So it must operate in a plasma. And so on Earth, that restricts it to operation within the ionosphere. Applications for EDTs. One is to deorbit spent stages or defunct satellites. This is called a terminator tether, and what happens is once the satellite has reached the end of its life, or the spent stage needs to be deorbited, it deploys the tether and then generates creates a current that generates a force opposite the direction of travel. This causes the orbit to decay until the point where aerodynamic forces will overtake and cause the object to re-enter. Similar to this, but generating the force in the opposite direction, is an orbit raising or orbit maintenance. One example for this would be for the International Space Station, as currently they use chemical propellant to reboost it. Since this method doesn't require any propellant, it would be an efficient method for orbital maintenance and reboosting of a space station or any other long-term mission. Yes?
Forgive my ignorance, but are tethers being used now, or is this just hypothetical?
Tethers have been used. There have been several unclassified experiments. I've been told that there have been ones that I can't know about. But ProSEDS was a NASA mission on, I want to say STS like 75. And so they tested deploying the EDT. It ended up snapping, but they did do some tests. There isn't widespread use, but it has seen experimental use.
Not projected that it will be used. They will be used more in the future, more regularly. Is that expected or just hoped?
Yeah, that certainly is the hope, and it has a lot of applications. And one of the next ones we've done a significant study recently on. So one of the big things is the cleanup of low Earth orbit. There is a lot of debris out there from spent stages for launches and defunct satellites in general. Well, it's not as bad as the movie WALL-E yet. It's certainly getting to that stage. So the cleanup of low Earth orbit is a problem that's going to need solving moving forward. The electrodynamic debris eliminator system is a concept that has been proposed for this cleanup. It uses, as you can see in the picture, there are solar arrays and a conductive tether along the length of the system. There are emitters at either end for the purpose that we talked about for operating in the ionosphere, and it has net managers as well. What the system does is it rendezvous with orbital debris, captures it using the net, tows it to low Earth tows it down to a lower orbit where the aerodynamic effects will cause it to eventually much sooner, and then repeats the process. So for this to be able to go between pieces of debris, it requires guidance for the orbital change. The existing guidance is either numeric, very computationally expensive, or is Semi-Analytic and has a simple magnetic field, which is inertially fixed to the rotational axis of the Earth. So the magnetic dipole will not rotate; it's fixed inertially. Here are the assumptions that I made going into the derivation of the guidance for this thesis. First was a spherical Earth. I was concerned with the changes to the magnetic field, not the obliqueness of the Earth and the gravitational perturbations that come from that. The Earth's magnetic field is modeled as a dipole. However, the dipole has tilt and rotates with the rotational period of the Earth. I chose 11.5 degrees as the tilt for the magnetic field. Modeling the magnetic field as a tilted rotating dipole is a more accurate method than the inertially fixed method. As everyone knows, magnetic north is not the same as the geographic north. And this will affect the guidance for an EDT, since it is dependent on the magnetic field. The other major assumption was that the EDT system is rigid and it does not vibrate. So there are no attitude dynamics with the EDT itself. So the tether will not stretch, and it is always pointed along the local and it is always aligned with the local vertical for the spacecraft. Also, eccentricities are going to be smaller than 0.065, as we discussed. The EDT requires it needs to operate within the ionosphere, which extends from an altitude of approximately 60 kilometers to approximately 1,000. Well, below 100 kilometers, the aerodynamic effects will cause it to re-enter. So I limited it from approximately 100 kilometers in altitude to 1,000 kilometers in altitude.
So just very briefly, the two tether assumptions are common in trying to make the problem tractable. Can you comment on how big of a quote unquote assumption those two things are?
When the forces are, basically, unless the force from the electrodynamic tether is operating directly on the center of mass, there is going to be vibration and there's going to be attitude dynamics, and they are not insignificant. When Nicholas Sadie has a paper which talks about controlling the attitude dynamics, and they can go between, I can't remember a specific number, but between 20 and 50 degrees off of the axis. And when you have that, the force is not going to be directly.
So then, at minimum, you can say that the problems, while open, are being addressed in the open literature.
Yes, they are being addressed, and there are methods to mitigate, even to a certain extent, what is going on here, where people have examined methods to dampen it so that you could just directly so that you could use something with an assumption such as this without altering.
So then your part is to say, okay, well, somebody else is worrying about that at the moment. I'm going to pick this
Correct.
problem here, which is the guidance on the current that produces the force.
Yes.
Cool.
Okay. Anything else? All right, so this is the system model. I apologize for the thinness of the lines, but this is the overall one where you can, this here is the rotational axis of the Earth. This is the dipole axis, and you can see that it's going to rotate around the rotational axis, and it causes the magnetic field lines to tilt off of the rotational axis. This is the EVT orbit, and we will get to a close-up of that here. And this is the coordinate frame that we're going to be working with, because the Gaussian variation of parameters are in the satellite coordinate frame, or RSW, where R is the direction pointing from the satellite to the center of the Earth, S is in the direction of travel, and W is orthogonal to both of them, or the outer plane. This is just the equation for the magnetic field of a dipole, where mu m is the magnetic moment. R is going to be the radius from the satellite to the center of the Earth. EM is the vector position of the vector direction of the magnetic of the dipole axis, and R is just the radial direction we talked about. These are the equations that define the rotating dipole, where beta is the tilt off the rotational axis, and alpha is the rotation of the magnetic field, which is one rotation per sidereal day. So this is in seconds, radians in seconds for the numerator and the denominator. And this is the transformation for the magnetic dipole. And you can see that alpha and beta are located there respectively. The perturbing acceleration for an EDT is defined by the Lorentz force. In this case, the L is the length of the tether, M is the mass of the spacecraft, I is the vector for the electrical current, and B is the magnetic field that we saw on the slide before. And since the assumption that the tether is always going to be pointed, it is always going to be aligned to the local vertical, we can make this assumption to make it not a specific vector, since it's always going to be aligned with R. So when I and B are substituted, you get the following equation for the final accelerations within the ET coordinate frame. Now this is a little bit of a monster, but we'll step through it. So these are the satellite parameters, which are the length of the tether, the current through the tether, and the mass of the spacecraft. Next, we have the parameters associated with the magnetic field. And so, where alpha, once again, is the rotation, beta is going to be the tilt, and you see mu m is the magnetic moment. And we have the orbital elements. Now, all of the perturbation equations use classical orbital elements, so they're going to be in terms of not radius and velocity, but semi-major axis, eccentricity, inclination, argument of perigee, and right ascension of the ascending node. And finally, we can see that there are only accelerations in S and W due to the tether always being aligned with the local vertical. The cross products cause there to be no forces in R. Once again, once libration is introduced back into the system, there will be forces in that direction. But for the purpose of this guidance, there is no acceleration in R. So then these accelerations are substituted into the following perturbation equations. These are the Gaussian Gaussian variation of parameters equations, which describe a differential change to all of the classical orbital elements. So when we substitute those in, once again, since there are no accelerations in R, those can be eliminated right off the bat. The terms in the yellow boxes are the accelerations in S, and in the green boxes are the accelerations to W.
And so reminding, again, the S's are
The S
in
is
motion.
in plane, W is out of plane. So,
Lateral.
yes.
Just out of curiosity, what are the S's and the W's? I mean,
Why the use of those letters?
I don't know, just RSW is the standard, is the.
I wrapped my brain around trying to figure out what they stood for.
No, I can't, so when I looked at the.
I was like,
Radio's obvious, but yeah.
So, Volato used it for, for the satellite coordinate frame, RS and W is kind of what it is.
S might be
Maybe
an arc
satellite
length.
track?
Omega, it is an angular velocity vector of the frame, is kind of that, but I don't.
So
That'd be
R
omega
is
rather than
radially
W, I don't
S
know.
satellite.
Anyway, it was just trying to keep track of, so I could remember.
Yeah.
I have no idea why that is, but yeah, for the purposes of this, well, and everything that uses R, S, and W, S is the direction that you travel, W is to your left.
Well, it's like airplanes. Why the left wing?
Exactly. Sorry. So for this presentation, we're going to be looking at the perturbation equation for the semi-major axis, because showing all of them doesn't really convey much. But all of the, it is the same process.
It gets repetitive.
Yes, it gets very repetitive very quickly. I can vouch for that. But we're just going to look at this. All of the processes are the same for the other orbital, for the other differential changes to the orbital elements. So once again, we have the satellite parameters, the parameters associated with the magnetic field, the orbital elements. You'll notice that in this substitution we have the introduction of P and N, which are the semi-lattice rectum, and the mean motion for the satellite. But up till here, it's just simple substitution for all of those.
And just real quick, same with the previous slide, when you say orbital elements, that you can translate that to effectively mean current position. So in the last, when you made the same presentation, there was news in there.
Yes.
So those are the time dependent.
Yes.
Which I know we're gonna get to. I'm just making sure I'm following.
We are going to, yes, we are 100% going to get to all of those, but yes, for these equations right now, all of the orbital elements are for that point in time, for that differential point.
And the only reason I'm bringing up is now that we've got into a differential time-dependent discussion.
Yes.
Everything, at least on this slide, is not time-dependent because there's no new. Later on, we're gonna talk about the time.
Correct.
Okay.
Yes, we are going to.
Or is there? I'm not sure that I would say that.
Okay, there's the alpha in there, but that's,
Well, okay, aside from alpha being time dependent, where is new in this equation, Scott? Do you have there's no, the one you had there.
Yeah, no, I'm,
Well, for one thing, yeah, there is.
there's bubbles in there.
they,
We got news everywhere.
yeah, they are all over the place. I apologize, this one's not translated correctly, I think that, yeah.
There might be, but it might not just be in that term.
Well, because A would be, I mean, it's in.
Yeah, if you look
No,
at.
I believe that there should be. There certainly is in the thesis itself. I don't.
Let's check.
Well, for sure there is one on your slide though. That's the one I'd like you
Oh.
to think of. Where is it in your slide?
Oh, yeah, sorry, R.
Yeah, so it's all buried.
R to the fourth.
Where's your R?
Maybe just briefly.
Oh, there it is.
Yeah, so
Oh.
R does have the position for true anomaly.
Okay, so there is,
And now it gets into all the expansions and all that sort of stuff. Yep.
Yep.
so then this is a time-dependent rate of change of A.
Differential, yes.
Okey-doke.
That is correct.
Which makes it hard to take credit for that.
Thanks for Point that out.
Oh, we're certainly going to,
There will be lots of credit taken.
Oh, okay.
So,
Particularly when we sign things.
So since we made the assumption for small values of eccentricity, therefore higher ordered terms of E are assumed to be negligible. So E squared, cubed, and so on. To further simplify the equations. The simplified equations, to go back, also the current has true anomaly as a part of that. It is solely a function of true anomaly and the argument of parity, and we will get into.
And that's your guidance
Right.
law. And once you make a guidance law, it becomes a time dependent.
Sure.
Yeah, okay, yep.
So, for this part, for the purposes of this, the orbital elements on the right side of the equation are assumed to be constant. Also, the movement between the previous equation and this one was that it was changed from a differential difference to a total difference for an initial time to a final time. So we integrated the equation between those two times to get the total change to the semi-major axis over that time for this maneuver. The orbital elements are assumed to be constant on the right-hand side because most of the time the change to them are going to be relatively small. And for just the purposes of coming up with an analytic or even semi-analytic equations, some simplifications had to be made, because if every single one of these terms is time dependent, which it is, but if you include that in the integral, there goes your analytic, or in this case, the semi-analytic method right off the bat. However, this integral is a function of true anomaly and of time. And any of the orbital maneuvers using an ET are long durations. So this isn't anything like your chemical propulsion, where you can assume that for all intents and purposes, that the delta V is instantaneous and you can just go from that point. These are hours, sometimes days long, and many orbits to complete the change. So it's impossible to decouple or to get true anomaly in terms of time, because you can assume that there are equations to put true anomaly in terms of time for short periods and for short time durations, but over hours and days it falls apart just due to the change in semi-major axis and all the other orbital elements. And as stated here, to evaluate the integral must be in terms of time or in true anomaly. We decided to evaluate the integral with respect to true anomalies. The equation you see on the upper right is the change of variables to get it from d time to d true anomaly. This is beneficial for many reasons. The largest one is that the short period perturbations drop out. When the integral is evaluated over a single orbit, all of the trigonometric functions such as cosine and sine, when they're integrated from 0 to 2 pi, the result is 0. So all of the perturbations during the orbit drop out, and the secular changes remain, because that's what we're concerned with. We're concerned with the total change, not that the semi-major axis does this and gets back to its starting point. So this is the resulting semi-major axis perturbation equation over a single period. And it is in terms, you can see that it's from 0 to 2 pi and is in terms of true anomaly. However, there are still time variables buried inside the integral in alpha, since alpha is solely a function of time. And so currently, could not perform the integrals. The method that we So the Earth's rotation is assumed to be small compared to compared to the orbital period of the EUT. The Earth, once again, it takes approximately 24 hours for one rotation, and EUT in low Earth, or any satellite in low Earth orbit is approximately 90 minutes. So to assume, so because of these differences in times, we assume that the magnetic field position was constant for a single orbit. However, at the end of that orbit, the position of the magnetic field is updated to its new position that is basically the time that it took for that orbit to occur. And this is done throughout the entire maneuver. So this is the variation of parameters of the equation for semi-major axis with a semi-constant dipole position. First off, you can see that the integral is solely in terms of true anomaly now, and can be evaluated. Second, you'll notice that the alpha terms are a function of the summation. The summation is for individual orbits, where eta at the top of the sum is the total number of orbits required for the maneuver. This is the formulation for the current to drive the secular changes to the orbital elements. Now, each coefficient is primarily associated with one orbital element. So you can see here that x1 is associated with semi-major axis, x2 with eccentricity, x3 with argument of perigee, x4 with inclination, and x5 with the right ascension of the ascending node. So increasing any of the, or changing any of those coefficients will primarily cause a change in that orbital element. This shows the evaluation of the integral on the previous slide, where instead of I, we plugged in this equation and evaluated the integral for semi-major axis. But you can see that it is not solely a function of x1. There's also a term of x2, which is associated with eccentricity. A simple way to think about this is if you're trying to change eccentricity, semi-major axis will change as well. This is true of all the other orbital elements as well. They all contain off terms for the other orbital elements. So the solution for the guidance law is non-trivial to try to change any of the specific orbital elements. So we reorganize the perturbation equations on the previous slides and for all of the other orbital elements to group them by coefficients. This is the equation on the previous slide, and here it is grouped by x1 and by x2. And this is so that we can assign basically a variable for each of those, where a11 is the equation in the red box, and a12 is the equation in the yellow box. A13, A14, and A15 are all 0 because there are no x3, x4, and x5 terms in this equation. So this same process to derive the equations to this point is performed pretty much in the exact same way for all of the other orbital elements. When that is finished, the following matrix is generated, which are all of the coefficients that we saw on the previous slide. For each aij, the rows are associated with the respective orbital element, and the columns are associated with their respective current coefficient, like so. So we get to where we can actually define the guidance. So if you define the changes to the orbital elements as this matrix, which are the changes to semi-major axis, eccentricity, argument of perigee, inclination, and right assumption of the assumption node, and define the tether current coefficients in the following matrix, the x1, 2, x5, you can correlate these two through the A matrix that was on the previous slide, where if you have the A matrix times the current coefficient matrix will return to you the total change to the orbital elements for that A matrix and for that current. Likewise, you can rearrange the equation to solve for the current and say, I want this change in, or these changes to the orbital elements. If you multiply the A matrix by that change, it will say it will return the values for the current to achieve that change.
So Scott, do we have any assurance that the A matrix will always be full rank?
It will, yes, it will always be full rank, or there'll be zeros. That's part of the, sorry, what do you mean by full rank?
Well, in other words, n independent rows are called 5 independent rows are columns.
Yes, it's always 5.
Independent,
sorry.
Independent,
Yes.
so it's invertible. in
Yes.
other words.
That's the question.
Sorry.
Whether we can be certain that it has an inverse.
Yes, it will always have an inverse. And
Why?
I mean, all of the
That hardly seems fair.
Math and engineering effects? What is wrong with this?
I'm trying to remember the rules for something always.
Well, let me just give you a little bit of a start here. Let's say that there was no coupling between the orbital elements. Can you describe the structure of that matrix?
So that would be just single values along the diagonal.
Yeah.
And
So those are all linearly independent because you could
yes, they're
write any vector in this
independent,
five-dimensional
it's fine.
space as a linear combination of those 5, right?
Right. And blanking on when you introduce elements to parts that are not the diagonal, when it wouldn't be invertible.
Well, when it's a linear combination, when you can write one row as a
Yeah, but if
linear
any row can be written as a linear combination of the rest, then it's not invertible.
Okay, I cannot guarantee with, 100% that you could not come up with one, but all of the equations are vastly different for the semi-major axis and the rest of the orbital elements. So if there was an off case that somehow you got one that where for example you got eccentricity and it was identical to that, I can't think of a single case because all of the equations, they're all dependent on true anomaly, but all of the equations for the secular change to each respective orbital element is vastly different from the rest of them. So I can't think of any time that a row would be.
Well, it would be difficult to approach the proof of that statement from that perspective. But you probably could come up with a justifiable argument just based on the physics of what these different equations represent. And I only raise that because whenever we do show the use of an inverse of a matrix,
Right, you have
it's
to
really
prove that
incumbent upon
it's-
us to
No, you're absolutely correct.
prove that that inverse exists. Or talk about the conditions where it does exist so that we can use it.
Right.
That's something we can look at for revision.
Yeah.
So, when are revisions due? July?
December, I think the final is due December 13th.
So you've got some time to at least investigate that.
Yes.
Yeah.
We're not talking a huge.
No, no, no,
Yeah.
I don't think it's a big deal.
No,
I just-
Well,
They're the DNC guys. I'm just looking at it like, I think the fundamental part of your question, does it fall apart at like E equals 0? Is that kind of like, do terms start looking?
Well, E equals 0 definitely falls apart, and Scott does address
Lots,
that.
yeah, lots of things fall apart when.
Okay, just making
Yeah.
sure that.
Especially when you're looking at orbital elements, I mean, E equals 0, it all goes out the window.
Yes.
Because
Well, you
then
said pretend
true-
Yeah, where are you?
Then true anomalies.
I'm somewhere.
I think that'd be worth looking at.
Yes, no,
So,
I don't have, that wasn't something that I addressed much of my time for. This work is an extension of previous work. Worked for them, excellent, moving on. But no,
That's why we have committee members.
Absolutely.
Especially committee members that teach math classes.
it's certainly, yeah.
I teach orbital mechanics, and this is, I trust math.
I trust math, I don't trust.
I just trust, but verify.
Yes, trust but verify. All right, so one thing to note is that every solution for the current coefficients is tied to a specific A matrix, and this A matrix is defined by a specific time of flight, which is correlated to the total number of orbits in eta, as we talked about before. So this is a factor because the spacecraft will have limited power on board. If you want to say change the semi-major axis by 10 kilometers, and you want to do that in a very short time period, the guidance will tell you that you can do it, but that the current necessary to drive that is going to be very large and could very well exceed the onboard limitations of the spacecraft.
But maybe furthermore also, I apologize, I didn't
No,
mean to
no, no.
but
Yeah.
several slides ago, you made a statement that in order for your guidance law to be derived, it is a secular
Yes.
change. And so if you wanted to do it fast, not just physical limitations from the spacecraft, but the assumption you made at the beginning
Yes.
would
It comes back to bite you, where you will achieve some change.
It
but
is
the-
it is convenient that you have a limited power supply and derive something that takes 10
Long
orbits.
Yes.
Yeah.
Yes,
Okay.
so that is part and.
Sure, blame the
parcel.
spacecraft people. That's how it always is.
I will blame the spacecraft people. So, conversely, for that same change, if you wanted to do it over a very long period of time, it's going to take much less current to get through. Part of the guidance is wanting to maximally use the current you have on board the spacecraft without exceeding it. This is the equation used to scale the time of flight for the A matrix. Imax is the current that is calculated. You can input any time of flight as your starting time of flight into the guidance. It will return Imax, which is the maximum current during that orbit, and then the I available is the current limit on your spacecraft. So if your Imax is under your I available, it'll scale it up so that you can reach it faster. If it's over, it'll scale it down so that you can not exceed the onboard power. And the process I described is what's in the flow chart there to write. It exits the guidance loop the current scaling loop when it reaches a tolerance, which is basically the previous time of flight and the new calculated time of flight. When they're close enough together, it says, hey, we've reached an optimal solution for this particular change. So this forces the time of flight to use the maximum available current without exceeding the power limitations.
So real quick, in one of those boxes then calculates, I want to make sure I heard it right, it calculates a non-secular I, so a true anomaly dependent I.
Yeah, all of I is dependent on true.
So Imax is not a secular term,
Sure,
Yeah.
you know, so there are, you know,
It squiggles in weird
yes,
ways.
it squiggles in weird ways, and the guidance just runs it from 0 to 2 pi, and it's like, hey, that's the max.
Okay, yeah. And I guess where I was running with that is it's not integrating it over the entire flight profile. You just answered my question, it's one orbit. So
Sure.
even though you're asking for multiple, not multiple, excuse me, even though you're asking to change, and I know we're gonna get to it in a moment, you're gonna update, let's say it's A, you're changing A. You're not going through the entire A to find the max I, but at least on this loop.
Sure. So, the current is solely a function of the coefficients, argument of perigee, and true anomaly. So, the only thing that could change, you know, once you know for one orbit, the current's going to be same for all of them, except for when the argument of perigee changes. So,